topic. I want to talk about the Millikan oil drop experiment. And this was a seminal experiment in the history of physics, done I think about 1905, maybe 1909, maybe earlier, right in the first decade of the 20th century by a physicist named Robert Millikan at the University of Chicago. And here is a schematic of his equipment. I'm sure his looked very different when he did it. But we're going to put tiny oil drops, which will fall through this hole into this space. This space is located between two plates. This is a full circle plate. You've kind of got a cutaway here. This plate and this plate, I have the ability to adjust the voltage to. And further, I can know what the voltage is. I can know the voltage between these two, and I can take a ruler and I can measure the distance between those two. Voltage, distance, I could know the field between these two. And I hope you recall from your experience with the simulation for fields that between two parallel plates, the field is uniform. This long bar would represent that this was the positive up here. We'll go ahead and mark that. And this would be the negative on this plate down here. So there would be a field which is directed. I'll let you put that on your worksheet. Is the field going up or down? But it's definitely uniform. Same strength everywhere. And if I knew the distance and the voltage, I could know the field everywhere here, and that's crucial to this experiment, that the field is known everywhere in there. I do have the option, they have not drawn it in this, there's a switch which will flip these and make that one negative and this one positive. Turns out that these oil drops that come in here have charge on them. They are microscopic, so I need a microscope to look at them. They are very, very small, and they have charge on them. They got the charge because an atomizer is like a little bulb that you squeeze and a fine mist of oil drops come out. We use it for putting perfume on. I don't know how often you put perfume on, but every time I put perfume on, I squeeze the little bulb and this fine mist of drops comes out. Well, in the act of rubbing against one another and rubbing against the sides of that tube, the oil drops come to be charged. That's not exactly how Millikan did it. He actually shone radiation at the oil drops, and the bits of radioactive decay would hit the oil drops and knock electrons on and off of them. But this is the way it is done in the lab equipment used in high schools. Okay, so they're charged, they fall through this hole into this region of uniform field. And some of these oil drops will be caused by the field to go upwards, and some will be caused by the field to go downwards. And then this arrow here speaks to the ability to adjust the field. So I will change the strength of the field until through the microscope I can see that I have gotten one of the oil drops to float. That is crucial to the experiment. And before we go on, here's another image. This is what the equipment would look like if we had it in our lab. I have taught at schools where we had it. It was a frustrating experiment to do, but very important. Here are the two plates, and here's an atomizer. You squeeze that bulb and the fine mist comes down this tube. You insert that. I think they would put it straight into this region, not up above and let it fall in, but maybe they do. Maybe there's a chamber up there that you can fill it and they can fall in. Here's the microscope for looking in there, and then you have the ability to adjust the voltage between the top and the bottom. Well, when the oil drop floats, that is going to be because the gravitational force pulling it down is equal to the electrical force that is pushing it up. And that if this oil drop has a positive charge on it, then I would like my electric field to be pointed upwards. And if my oil drop has a negative charge on it, I would like the electric field to be pointed downwards, because an electric field downwards would push a negative thing up. But at any rate, I get this electrical force going up, and it's in equilibrium with the gravitational force, the weight of the oil drop. The gravitational force is equal to the mass of the oil drop times the acceleration due to gravity. The electrical force is equal to the strength of the field, which we just argued that by knowing the voltage and the distance between the plates, I know the strength of that field, which is uniform everywhere between the plates. And here would be the charge on the oil drop. Well, through the microscope, I can measure the diameter of the oil drop, and knowing the density of the oil and assuming that it has made a sphere, I can determine the volume of the oil drop and multiply the volume times the density, so I can know the mass of the oil drop. I know G is 9.8. I know the field strength because, here you go, I know the voltage and the distance between the two. Notice I've lost the negative here because I just found it inconvenient. And so the only unknown here is Q. And that is what the Millikan oil drop experiment is all about. That he found the charge on an oil drop. And then he did it again and found the charge on another oil drop, and another, and another. And he collected thousands. I don't know that for a fact, but he collected many of these oil drops. And then he plotted how many of them he found versus what charge they had. And the graph looks like this. And it would be very neat if we were sitting together and I could probe you to say, okay, here are the results of these thousands. This would be that maybe he found 500 at this charge, and 270 at that charge, and 200 at this charge, and at all of these charges, how many oil drops he found? Many oil drops at these charges. And I would ask you to look at this graph and say, okay, what is interesting about this graph? What is intriguing? What is noteworthy? And there's several things that I hope you would see. We'll go ahead. We'll play a game with this. Please put this on your worksheet. Can you list all the things that are worth noting, that are latent with meaning about this graph? So stop the show, make the list, start the show again. But leave your list alone. I want to see what it looks like. Don't augment it based upon what we say here. If you put nothing into that list, I'm going to take a point off your grade. Alright, so the show has started again. One of the things you notice is that these spikes exist. There are spikes, by which we mean there are places where we found those charges, but there's a whole bunch of places where we don't find charges, that some charge values do not seem to be occurring. Only certain charge values occur. And then I also note that those places where charge values occur seem to be about equally spaced. That there seems to be a smallest charge that occurs, and all the other charges are twice as much charge, or 3 times as much charge, or 4 times, or 5 times. That is very interesting Millikan got very intrigued by that. What you are seeing is a quantum phenomenon. That charge comes in lumps. We call these lumps quantum. And you can have one lump of charge, or two lumps of charge, or three lumps of charge, but evidently you cannot have a fraction of a lump. That's what it means to be quantum. That it comes in a certain size quantity, and you can't have fractions of that quantity. Quantum physics, right here. Now, if we look further, this value here is between 1 times 10 to the minus 19th and 2 times 10 to the minus 19th. Maybe a little past halfway. This one here is maybe what? 3.2 times 10 to the minus 19th. Maybe 4.8, 6.4, 8. Whoa. All of these values I'm getting seem to be multiples of this value, which seems to be about 1.6 times 10 to the minus 19 coulombs. Surely you recognize that number. I want you to put it on your worksheet. What is that number that we have twice of and 3 times of and 4 times of? Start the show again. Don't you make up something. You say, oops, that was a 10. You say it's, wow, all my ones went away. Okay, they're back. 1.6 times 10 to the minus 19th coulombs. You make up something. Try to make it reasonable. But then I want to see what you came up with. Please don't change it when you start the show again. And now the show has started again, and we recognize that is the charge on an electron. If it was negative, it would be the charge on an electron. If it was positive, it would be the charge on a proton. They both have the same magnitude size charge. Why that amount? That's a question for the mysteries of the universe. But all electrons have this magnitude charge. And in fact, all Millikan found was that when you charge an oil drop, you put one too many or one too few electrons on it, or you put two too many or two too few electrons, or three too many or three too few electrons, but it is not possible to put 1.5 electrons or 1.25 electrons. You cannot have a fraction of an electron, and that's why it comes in lumps. The size of the lumps are the charge on an electron. So, I am going to ask you, when it comes time to grade you, to know 3 things about the Millikan experiment. I would ask you to know the design, the equipment of the Millikan experiment. I would ask you to know these equations that were used in the Millikan experiment. And I would expect you to know the results of the Millikan experiment, which was, and I would accept 2 different answers as equally valid. You could say the Millikan experiment found what the charge on an electron was, or you could say that the Millikan experiment found that charge was quantized, was a quantum phenomenon. Either one of those would be good answers. Next, I want to talk about equipotentials. This is a word that spell check keeps saying does not exist. But I'm going to use it all the time, and I want you to kind of break it apart. What do you think it's talking about? And of course, it's talking about equal potential, meaning having the same voltage. Suppose this image here was of an equipotential surface. That is, this membrane represents a series of locations that all have the same potential. So if, let's see, we go red here. If I start at location A, and we'll make this a little bit bigger, and I go to location B, and they both lie in this equipotential sheet, what is the potential difference between those two? And it turns out that it doesn't matter how I get there, that I could stay in the sheet the whole time I go there, or I could go up above the sheet and down below the sheet and snake my way around there, that if I go from A to B, I'm going between two places in the same potential, and so the potential difference is zero. Now let's consider making the trip in the sheet. We'll go with orange. Here's the trip. Boop, boop, boop. And I'm staying in the equipotential the whole place from A to B. What is the expression we have for voltage as a function of field strength? And I'd like you to stop the show and write it down, then start the show again, and I hope what you have is V is equal to negative E dot, what was it, D we used? D. Well, that's very interesting in this situation, because the potential difference between A and B, AB, is zero. But that does not mean that the field between A and B is zero, nor is the distance from A to B zero. So how could you take two non-zero quantities and multiply them together and get zero? You write that on your sheet, then start the show again, and I hope you recognize that it must be that the field is everywhere perpendicular to the path that you are following. If the path lies in the sheet, then the field must be everywhere perpendicular or normal to this sheet. That is a truth that we need to embrace. If you have, say, a positive and a negative, we'll get some color here, charge, then they have a field which looks like this. And we're not done, of course. We need to put arrows on that field. This would be the electric field for those two charges. What then would the equipotentials look like? Suppose I have an equipotential that passes through that point. Well, it's going to go, I'll put this on your worksheet. You could try your hand at it and then feel very proud if you got it right. We'll start the show again, and you ought to have a sort of a surface that always passes through a field perpendicular to the field. It's not an exact science here, but there would be an exact place where that equipotential would go. I like it better dotted than solid. And it would go like that. And then there would be another one out here. And there would be ones over here. And there would be this whole family of equipotentials going here. See if I can get one more in. Which you ought to be able to recognize that this is the equipotential for opposite charges just as easily as those blue lines would be recognized as the field for opposite charges. Everywhere perpendicular to the field. Very, very important idea. How much? Oh, what about this question? What about the surface of a conductor? We ought to get rid of all this, but I don't know how. What if you had a conductive sphere? Or maybe it's not so uniform about itself, but I have this blob that is a conductor. What does the field look like at the surface of a conductor? And we already established that idea, so we played like a quiz. You put it on the worksheet. What does the field look like? And I hope that you recalled that the field at the surface of a conductor is everywhere perpendicular. What was the field look like inside of a conductor? And the people cry, there is no field inside of a conductor, but at the surface the field goes perpendicular. And we made the argument that if it wasn't perpendicular, if it had some component parallel to the surface, that would cause a rearrangement, which would continue until the field parallel was zero. And the same argument for no field inside. But isn't a conductor an equipotential? Yes, it is. Everywhere the same potential on a conductor. So we would naturally expect the surface of a conductor is an equipotential. The field should be perpendicular to it. Nice results. Good stuff. Right, I want to do some more. These are two conductors, and I'm going to put some charge on them. That I'll put a charge of 4 positives on this one by taking away electrons, and a charge of 4 positives on this one by taking away electrons. So these two things have the same charge. It is not actually true, but it is close to true, that if you were to take a wire and run it from one of these to the other, that very little, I would like to say no, charge would move. Why? Because these two things are at the same potential. They're actually not, but to get into the details would mess up my argument. And the argument is leading to a valid point. So no charge would rearrange when you connect these two. Not strictly true, but we'll say. So that's one wire. Then I'll take another wire and run it between the two. And another wire. And another wire. And I'll keep running wires between these two. And no charge is going to redistribute, or very little distribution. Actually, if this sphere had twice the radius of that sphere, not to scale here, then, and it had the same charge on it, it would have twice the voltage here as there. But yeah, no, let's forget that. No charge redistribution. Well, the result would be, and I hope I made it very clear that that's not true, but still there would be minimal charge redistribution, and the result is that I have made a thing with a point. And you remember that for things with points, you got highest charge concentration at the point. So this is kind of an argument for why that ought to be. This is definitely the reason why the Van de Graaff generator, the top of the Van de Graaff generator, was made as round as possible, and then you have that stem coming up into it. They want it to be round so it has no points, so you will get no places where charge will concentrate. If you made a Van de Graaff generator, here's the plastic post, and you put a cube on top of it, then the charge would concentrate at this corners and it would all leak off. I don't want it to leak off, so I make the Van de Graaff generator have as little corner as possible to keep the radius of curvature as much the same as possible. Final topic. I want to talk about electron volts. This is something that you work with in chemistry a lot. The energy of reactions is often given in electron volts. And I have just spoiled my surprise, but I want you to consider what the units of a volt are. Well, Mr. Houghton, they're volts. Yeah, but what is a volt in terms of other units, in particular in terms of joules? And then what kind of quantity would you have if you took that which a volt was and multiplied it by charge? And you're no fun. That a volt is work per charge moved, a joule per coulomb, and if you multiply that by coulombs, you get joules. So this is a unit of energy. This is something I want you to recognize. However, I didn't multiply a joule per coulomb, which is what 1 volt is, by a coulomb. I multiplied it by the charge on an electron. That's what a lowercase e is, the charge on an electron, which was 1.6 times 10 to the minus 19 coulombs. So this quantity of energy here is equivalent to 1.6 times 10 to the minus 19 joules. It is a very, very small fraction of a joule, very appropriate for the energy of one oxygen atom combining with one other oxygen atom. You need to be able to convert between electron volts and joules, and basically you either multiply or divide by this number depending on whether you want to make it bigger or smaller. For example, suppose I'm talking about 26 electron volts, and the problem is, how many joules is that? Well, I hope it is clear that this number ought to be significantly smaller than 26. And so what I need to do is to multiply by this number. So you end up with, well, why didn't we make this be 20? So we end up with 32 times 10 to the minus 19th joules. Much smaller when you measure it in joules. Although it is equal. And vice versa. If somebody said, hey, I got 20 joules, That's a hard number. Let's say you had 32 joules. And they say, how many electron volts is that? Then I realize that this number here is going to become very, very big. And these units very small. So I would need to divide this by 1.6 times 10 to the minus 19, and it comes out to be 20 times 10 to the 19th electron volts. It gets much bigger. Alright, that's all I got to say. Go to bed.